Hi, in this video I will be discussing the concept of equilibrium constant and the motivation behind the formula for the equilibrium constant. And the prerequisites for understanding this video is chemical kinetics, the basic knowledge, and the concept of equilibrium reactions. So you might have learned that there are two kinds of reactions, reversible reactions and irreversible reactions. But in reality, there is nothing called irreversible reaction. So both the forward and backward reactions are possible, but in some cases the tendency for the backward reaction is much less than the forward reaction. So practically these reactions are, we term them as irreversible, but there are no irreversible chemical reactions. So let us consider an equilibrium reaction where a compound A reacts with two equivalents of compound B to give this compound AB2. So the equilibrium constant for this reaction K is equal to the partial pressure of AB2 divided by product of partial pressure of A and the square of the partial pressure of B. I am assuming that A, B and AB2 are gases which are enclosed in a closed reaction vessel. So this is the equilibrium constant for this reaction. So what this means is that when this reaction reaches equilibrium, that is, the concentration of A, B and AB2 remain constant and don't change with time, then this value will remain a constant independent of the actual values of A, B and AB2. So suppose this reaction vessel is in equilibrium and I add some amount of A. So now the system is not in equilibrium. So the forward tendency is more. So the reaction proceeds in a forward direction to some extent where it is in a new equilibrium. And this quantity, that is the partial pressure of AB2 divided by the partial pressure of A and the square of partial pressure of B, is the same as the initial value. So this quantity is independent of the actual values of partial pressure of AB2, A and B at a particular temperature. So I will give a brief intuitive derivation for why this value will be a constant. So before we proceed to that, there are two kinds of reactions, elementary reactions and compound reactions. So elementary reactions are reactions where the actual mechanism of the reaction is where the reactant molecules collide with each other and give the product molecules. So for example, methyl bromide reacts with chloride anion to give methyl chloride and a bromide anion. So in this reaction, a molecule in the solution, a molecule of methyl bromide collides with a molecule of chloride, and if it passes a certain activation energy barrier, these product molecules separate out. So there is no more to this reaction than just the collision of these two reactant molecules. So this is an elementary reaction. So suppose we consider combustion of benzene. 2 benzene molecules plus 9 oxygen is in equilibrium with 6 CO2 plus 6 H2. So for all practical cases, this is an irreversible reaction since the forward tendency is very high. So it is probabilistically impossible for 9 molecules of oxygen to collide with 2 molecules of benzene to give this product molecules. It is a highly improbable situation. So the actual process in which this reaction occurs is, it has several intermediate steps by which these reactants react to give the products. So this is not a single step reaction. So elementary reactions are single step reactions where the reactant molecules actually collide to give the products. So supposing that this equilibrium reaction is not a single step reaction, and hypothetically the mechanism of this reaction is a molecule of A reacts with a molecule of B to give a molecule AB, and a molecule of AB reacts with a molecule of B to give a molecule of AB2. So these two are elementary reactions. So let us denote them as 1 and 2. So let us consider the first reaction. So this is an equilibrium reaction. So by the laws of chemical kinetics, the rate of the forward reaction, is equal to product of the rate constant for the forward reaction and the partial pressures of A and B, and the rate for the backward reaction is equal to product of the rate constant for the backward reactions, small k, and the partial pressure of AB. So when this reaction is in equilibrium, the concentrations of AB and AB2 don't change with time. So this means that the rate of formation of AB is equal to the rate of depletion of AB. So the forward and the backward reactions are equal. So these two are equal. So we get Kf by Kb equal to partial pressure of AB divided by partial pressure of A into partial pressure of B. So this is called the equilibrium constant for this equilibrium reaction. So note that this has the same form as this. This equilibrium constant is equal to the product of the partial pressures of the product compounds divided by the product of the partial pressures of the reactant compounds. Each partial pressure raised to the number of molecules, number of equivalents in the reaction. So let us write the equilibrium constant for the second reaction. Similarly, the equilibrium constant for the second reaction will be equal to the partial pressure of AB2 divided by product of partial pressure of AB and the partial pressure of B. So notice that when you multiply K1 and K2, you get it as equal to K. So K is equal to K1 K2. So when this reaction is in equilibrium in a reaction vessel, AB and AB2 have a constant partial pressure. So K1 will be a constant independent of the temperature, independent of the actual pressures, and K2 is a constant independent of the pressure of these compounds. So K1, K2 will also be a constant independent of the pressure of AB2, A and B at a particular temperature. So this value is a constant irrespective of the pressures at a particular temperature, and this constant is called an equilibrium. It's called the equilibrium constant of this reaction. So now for any general reaction, suppose A molecules of A react with B molecules of B to give C molecules of C and D molecules of D. There may be more reactant molecules and product molecules. So this value, the partial pressure of C is raised to the C to partial pressure of D raised to D divided by partial pressure of A raised to A multiplied by partial pressure of B raised to B is a constant, and this is called the equilibrium constant for this reaction. So you might have seen this formula, but I have given an intuitive way of why this value is a constant. You can break this up, you can write down the mechanism of this reaction consisting of its elementary steps and multiply the equilibrium constants for each of those elementary steps. That will be equal to this.